Right, everybody, welcome to P12C. Let me just get myself a pen up. So this is the third lesson in this series, and we're just going to look at magnetic forces in their own right. Starts with a couple of questions that might be relevant for application, and that'll make some more sense in a sec. So, Tom, could you do me a favour? Could you read this out nice and loud for everyone?
Your parents have tasked you to supervise your uncle, DIY Dave, who thinks he is pretty mean with a drill. His fancy electrical cable finder has run out of batteries, but he carries on anyhow. You just returned from DLE with a compass. Describe how you might check the power cables before he plunges you into darkness.
Okay, so we all have somebody in our family like this who likes to get a drill and drill holes. Okay, in walls there are cables, and invariably they hit them. So you don't have a magic cable finder, but you do have a compass. How would you use the compass to help DIY Dave? Go on then.
Is it something like the direction of the needle?
Okay, so we think the needle might move. Why? Hold on. Yeah. Anybody else want to add in something here? Why would the needle and the compass move? It will. You are right. What's magnetic?
Yeah.
You're on the right track, but do you know why? That's the question. Can you want to help her out? What's going through the cables, guys? Electricity. What happens when electric current flows? We get a... What do we get? What are those circles wrapped around the... No, that current's flowing through the cable. What kind of field is it? Magnetic field. What will happen if you put a compass in a magnetic field? Yeah, not quite north. Bit of a misconception there. Go on, Will.
If you put it near a magnet,
Yeah.
it will point, can't explain it, but it will point towards the field lines.
Field lines. You are almost 99% of the way there. It will line up with the field lines. I know roughly what you're trying. Just be careful saying north will point a certain direction. Okay. Oh, we had a 2-minute time on that. So, what we can take from this, guys, is you can use a compass to find electrical cables. What's the catch? Will it find every single electrical cable?
No.
Why not? This is the third mark. No, that's nothing about how many. Anyone want to ponder pose a suggestion? What did I tell you you needed flowing through the cable? Current. Is current always flowing through every cable? So if the light switch wasn't turned on, would you find the light cable in the wall? No, that's the risk, okay? So it's a little, no, I'm not suggesting you go try and find electrical cables with a compass in a house. It's not a particularly efficient way of doing it, but this is about understanding how magnetic fields work, how you can find them, etc. Okay, just reiterates. You could always get a whole bunch of iron filings and throw them all over the wall. It's a bit messy though. Right, let's move it on. So, things we need to... This, guys, could you just give 3 bullet points at the top of your paper, because these are 3 massive ones. We're going to do the right hand rule. We're going to do the left hand rule, so when you start doing revision or practice questions, I want you to be able to find these bullet points. Bullet point these for me, please. We're going to do right hand rule, left hand rule, and forces on a wire in a magnetic field. Now, if I showed you that question now, you'd all look at me blankly, but by the end of the lesson, you're going to be able to answer it. Okay, we're going to have a look at Fred and Bill again. Anyone remind me about Fred and Bill? Who's got good recall? Who's Fred and Bill? They're all looking a bit blank. Those of you at home, if you have a look in your revision notes, who's Fred and Bill? Force equals magnetic flux times current. And what's the L stand for? Wow, that was amazing. It's like you said something, like your lips moving in a very different voice. She did say it, by the way.
For length.
Length. Okay. So we will go on Fred and Bill again. So you do need these. These are all three things you need to have on your revision material. And by revision material, I mean a single piece of revision material. Whether that's flashcards for P12 and P13, or you do it on one big A3 sheet, I don't mind, but you need to have a singular piece for this. Any questions on this before we move forward, guys? Everyone knows what we're up to? What we're going to do? Let's do it then. Right. So magnetic fields on a current carrying wire, which is what we were just talking about. Which one did you miss? I can go back. I can't go back actually. It overwrites the whole thing. Okay, so if we can generate a magnetic field on a current carrying wire, what will happen to the magnetic field if I increase the current? Let's use some common sense here. What do you reckon if I increase the current? What's going to happen to the magnetic field? What do you think? No, don't shout out. What's your intuition telling you? It's not a trick question, I promise. What do you think would happen to a magnetic field if I made more of something happen, more current flow? It's either going to get stronger or weaker. Which would you go with? Stronger? Anyone else? Stronger, weaker? What are we thinking? Stronger? Yeah, it makes sense, doesn't it? And you are right. It would be definitely stronger. Okay, I don't know if these are going to come up. So I'm just going to do magnetic field will go stronger. Absolutely. What if I make the wire shorter? What do you think if I make the wire shorter? What would happen to the magnetic field then? I'm either making it stronger or weaker. What do we think? Weaker, stronger? What did you go weaker?
Because there's less of the wire for current to go across.
Makes sense? Less wire, less magnetic field? Yeah, you're absolutely right. So in this one, the magnetic field would go down. Okay, the strength of the magnetic field. If I use the material with easier to align electrons, now that's intentionally clumsy. What am I talking about there? Talking about a couple of different materials we could use. We've talked about this when you saw it with the nail. What was the nail made out of?
Iron.
Not quite iron, close. It's made of iron, but we turn it into, we add a few things to iron to make it. Buildings made out of it. Steel. Okay. What's the difference between steel and iron then? From a magnetic point. Anyone paying attention? Go on, you know.
I don't know which one it is, but isn't one of them really like
Help her out. Sorry?
Iron can't hold this magnetic field for that.
Very good. Iron's very easy to magnetize, but doesn't hold it at all when it's doesn't have an induced magnetic field around it. So that's why permanent magnets are steel, and electromagnets, which we did a lot of work, are normally made from iron. Yet they're mostly, steel is mostly iron with a few bits added to it. But it's about the ability to rearrange the electrons. We can rearrange the electrons in steel, but it takes a lot of work. But once they're there, they stay there. So they make good permanent magnets. Iron, really easy to align all the electrons, but as soon as we move the magnetic field, they all go back to where they were. Is that making some sense? Okay, all right. So if we use easier to align electrons, we would expect the magnetic field to go up. Okay, so these are just we're starting to look at some of the applications of what we're talking about. Okay, so there we go, and I'll break those up here. Go to the next one. Right, some questions for us to have a go at, please. You'll need your calculators out. And you need to score me. So this one is worth 2 marks. This one is worth 2, and this one is worth 3. And I need you to get me at least 4 marks worth, please. So you can choose any questions you like, but you need to get at least 4 marks worth. and I would sincerely hope that you all have a go at the first one on the left. It looks really simple, but it's done incorrectly quite often because it's about how to use your calculator properly, which helps when you have a calculator.
No, no, no.
Oh well, you can do this, the middle one, the one on the right hand side, with that calculator, I suppose. And if you need help, give us a shout. So I'll set a timer for this, just so if you're watching this at home, you get some idea of how long it's going to go for. You can obviously pause and then fast forward. I reckon I'll give these guys a 3-minute timer from now. So to 4:30 on the clock. Tom, which ones are you doing?
I don't know. I was probably going to go with the middle one.
Have you done the one on the left first?
No, I haven't.
Have you done anything first?
No.
Okay, let's start on the one on the left then.
Okay.
Start by using the fraction button, and then putting top and bottom of that fraction button into your calculator. So you get the whole question in your calculator screen in one go.
Okay.
Alright?
Yep.
As soon as you do that, the chances of making mistakes drop dramatically. You can do the middle one without a calculator. You with us?
Yeah.
You're staring at it.
Yeah, just looking at
Okay, start. What do we do at every physics problem? First thing you do,
it. Right equation.
write the equation. Tells you the equation. So write the equation down.
Wait, so the first one, would I just put that as a fraction?
Yeah, I'd use the fraction button in your calculator. It means you can put the whole thing on the screen in one go.
Okay.
Don't have to do it that way. I just find people make less mistakes when they do. Let me know when you get an answer, guys, and I'll give you some steerage if you go wrong. If you get syntax error, I get to laugh a little bit. I won't laugh, I promise. Calculator? You done it? Yep. What'd you get? Well done. Go on to another one then. Your choice. Sophia, have you done the one on the left? What'd you get?
0.125.
How you doing, Tom?
Yeah, I'm going syntax error.
Right, I'll come over. Now we've got to keep 2 meters distance. So through your calculator.
I swear it's 1 meter.
Okay. So you can press the go to button to do the arrow. It doesn't like something you've done there. Oh, there's 2 spots there, I think. Oh, so that's. So leave that times. Okay. Oh, well, you've done the same thing there. So use the get used to using the times 10 to the power of the 9. You going on that?
Thank you.
So this is why we do this. So you're not doing that in the middle of it. Imagine trying to figure a syntax error out in the middle of an exam for what is effectively 1 mark. You'd feel a bit silly, wouldn't you?
Yeah.
This is why we're practicing physics. This is why we need a calculator. How did we go on the first one, guys? What'd you get?
0.125.
Anyone get anything other than 0.125 or syntax error? It does happen, that's why we practice. What'd you get?
I got a fraction as well.
Okay, if you get a fraction, be cautious of what the question is asking for.
No, I got the other one, but then when I pressed the thing,
Yeah, because if you set it up as a fraction in your calculator, it will often give you the fraction first as an answer. As long as you know how, as long as your brain goes, I probably don't write 1/8 down. I probably need to switch it to 0.125. Then you're golden. That's good. Right. What do we get for the second one? Who's got an answer for me? Alex.
I got 8,500.
Looks pretty right to me. Anyone get anything different than 8,500? except it's not right. Dun dun dun. Is it 8,500 elephants, chairs, tables, windows? 8,500 watt joules. Big capital J, please. Okay, energy always joules. Nah, that's a bit of a trick one. Not telling you to tell you what the unit is. Giving you everything you need to do. Fairly straightforward, but you would lost a mark. Right, did anyone try the one on the right hand side? Now if you tried this at home or you're looking at it, you might realise that this is the mirror image of what we've done so far. So we've been talking about magnetism and how to create magnetism, but what happens if you, so using electric currents to create magnetism, what if you use magnetism, can you create electric current? Well, the answer is yes, and that's P13. But we haven't got to P13, we're a couple lessons away from that yet, but it's just to give you an idea of, if you can get your head around how magnets work, P13 is a doddle. Okay, so they're just mirror images of each other. Any questions before we move on, guys? Yeah, all good?
Wait, what was the equation for A equals?
What was the...
I managed to work it out, but what does the A equals QV stand for?
Okay, E stands for? Always. Yep. Do you remember what the V stands for? Voltage or potential difference, which is given to you. And the Q is the start of the question?
The charge.
Charge. Okay. It's just the letter, standing letter. You could put P or elephant in there. You could put anything you like there. It's a standing letter that we use to represent charge in an equation. The really good thing about E equals QV is easy to remember because it almost spells equivalent.
What's the
Voltage or potential difference. Yep. Okay, let's move. Okay, welcome to the right hand rule. Everyone get your right hand. This is where someone puts their left hand up. Get your right hand. Now it's going to look like I'm holding my left hand up to you. I will do it backwards to show you. Now for those of you at home, this gets quite amusing to me from this classroom because people start moving their arms and bodies around trying to align there. So we're going to pick something in this room. It's a lot easier in a science lab. Let's pick, goodness me, there really isn't anything that goes top to bottom. Let's pick that piece of conduit that goes along the ceiling that way. Can everyone see the one I'm talking about? Yeah, you guys have probably got the hardest view. That is going on that way. We're going to assume there is current going down it that way. So I'm pointing in the direction of current and I'm going to line my thumb with the direction of the current. So everyone put your thumb in the direction of the current. You've got to use your right hand because if you use your left hand it's going to go horribly wrong. Your fingers are the magnetic field. Okay, so the magnetic field will be around it, but your fingers will point in the direction of the magnetic field. So if you were drawing lots of circles around that piece of conduit going down, your fingers would be the arrows, the tip points of the arrow. Questions? You're all looking a bit blank. Some of you are now working on your nails. All good? Okay, so which way is the magnetic field going around that pipe as it goes down the wall? That way? So if we were looking at it from that way, would you say clockwise or anti-clockwise? Try again. The other one. It's 50-50, wasn't it? Yeah, clockwise. And that's really important because, does it make sense? So your fingers would wrap around it, the cable. Yeah? So your fingers are now making a circle, and your finger points in the direction of the arrow. Okay? Does that make more sense?
Yeah.
See? I will. If you tell me that it doesn't make sense, honestly, I'll find another way to explain it. You just have to be honest. Alright? Is there anybody else who's still thinking, what on earth is he talking about? So, that one on the left, guys, that's how you'd see it in a theoretical drawing. The one on the right is obviously your best thumb, and you get bonus points for the best drawing of a hand and thumb, please. I am the world's worst drawer, and none of you will beat me. Okay? So I clearly rip off the diagrams from Google because I can't draw, but you just need to know that the current thumb goes in the direction of current and field lines.
So we have to draw hand.
Yes. I like doing this because it levels people out. They start to think, I can't draw either. That's alright. As long as it looks roughly like a hand, you're okay. Sphere, use your right hand. That's your left that you just held up. It's alright, we'll do the left hand wrong a bit. For those of you at home, guys, I appreciate you can't see a lot of what we've been talking about in the room, but all you need to do is line your thumb up in the direction of the current flowing down a cable, wrap your fingers around it, which would make the circles around the cable, and the fingertips will point in the arrow of the field. So in this instance here, I'll try and draw the top here. So you'd end up with a field around a cable that looked like this. So I'm just overlaying it over the top. If our current does that, I for current, B for field. Hopefully that makes sense to you. This is where I find out who's going to get a 7 at GCSE art. Some people just have a knack for it. At the end of the day, as long as you understand what you are learning here, it doesn't really matter if you can tell, you know, a hand with 18 fingers. It's fine, it doesn't make any difference. Chip fingers, yeah. I have had people's diagrams before I've looked at and gone, no, that's really that bad, you're going to have to do it again. But it's very rare. At the end of the day, you just need to know it looks like a hand. You can even write hand if it gets that bad. Right, we've got another 30 seconds, guys, before we move on. How are other lessons last week? Yeah? Still going full force with other subjects? Yeah. I think you might see it drop a little bit this week, but not by a lot. Yeah. I was just talking about how you're finding subjects. There's still, you know, are you getting lots of stuff to do? And have you not got it already? We posted home all the booklets to you. They're not too thick. They're only about like yay thick each. They're being posted to you. It's homework to do every day for the whole holidays.
Really?
Yeah.
Wow.
Oh, I can't give you a straight face.
Well,
Of course I'm joking.
Oh, please.
Right. Okay. Now because I'm recording this, I have to now caveat it that that was a joke. There is no booklet being sent home for those of you who heard me say that. However, I will say this. Stuff that you have let slide because lockdown has been really weird for all of us. If you've let it slide, don't start convincing yourself I'll do it sometime during the holiday, because you will not. I was your age once too. I know dinosaurs were walking the earth at the time. Don't mock my age. But I knew if I just said I'll get to it during the holidays, it wouldn't get done. You have to be very honest with yourself and say, what do I want to get at the end of my GCSEs? What do you want to get at the end of your GCSEs? What grade do you want to get for science? Someone throw me a grade. 5. I wouldn't be happy with a 5 for you. I'd want to see at least a 6. Genuinely.
Okay.
But that's only because I think you could get it on a good day. But yeah, 5 would be a good result. What else? What do you want?
No, 4.
4?
I'll take
Okay.
4, yeah.
Okay, a 4 is a pass, but it's a pretty average pass, guys. But what you could do is say, I'm going to make sure I'm definitely a 4, and if I have a good day, I'm going to hit 5s. Do you hear the difference that we're sort of proposing there? This isn't about saying everyone must do their best. It's not that kind of nonsense. It's about saying, what will you be happy with on results day in a year and a bit's time? What will you be happy with? Go, I got a 4, but I really should have got a 5, because that's a horrible feeling. There is nothing better than opening and going, oh wow, got a 5. Awesome. That little bit of extra work I put in the summer holidays, because Mr. Gregson told me if I wanted to do well, I actually had to work for it, paid off. That's the sell here, guys. There is one thing in common for students who get U's, 1s and 2s. And I mean this, and I hope it doesn't come across as too brutal. But the students who get U's, 1s and 2s because there are very few students, and none that I would know of in year 10, who couldn't get higher than a 2. But there will be some who get lower. There will some people who'll get 1s and 2s. It's because they focused somewhere else. Now, I hope that's another subject. Some people, unfortunately, they focus on doing absolutely nothing, and they do it very effectively. But your 3s, 4s and 5s are the people who are honest and say, do you know what, I'm not very good at science, but I did try, I did practice. I took the information that's given to me and I kept pushing, I kept trying practice questions. That's all we'll ask of you. If you turn up with the right attitude to practice, we will back you 100%. I will take a hard-working student over a bright student any day of the week. I have an A-level physics class full of kids who got 7s, who should have got 9s. Whereas on results day, I've shaken, well, yeah, it sounds silly, doesn't it? But if you're that bright that you can do it, then a little bit of hard work shouldn't be a big deal, should it? That's the difference. Whereas I've had students on results day who've come over and hugged me because they got a 5. It made their world. And then, do you know what? I'm happier about the 5 than I was about the 7. Because they earned it, they worked hard for it. You get nothing in this life without hard work, guys. GCSEs is not about how smart you are, it is how hard you work. And by work, I don't mean slogging it out, I mean just practicing. So when they give you practice questions, you take them seriously. Your mocks this year, in case it's not abundantly obvious, are going to be pretty important, just in case. You know, you could be the year that does the mocks, thinking that that might end up as your result, should schools be shut again. Okay, and I'm not saying they're going to be, I really hope they're not, but there's always that possibility. So you need to pull the stops out for the mocks. Okay, that means having a timetable for yourself. When am I going to do physics work, when I'm going to do maths work, when I'm going to do some English work, and being honest with yourself, make it achievable, that you can actually do it. Not, I'm going to do 8 hours of study every evening for 7 days a week. Who's kidding who? Right, you got to make it realistic, and you have to have fun as well. You have to plan in sports. You have to plan in. Don't cancel your life. Okay, just make sure your life is balanced. That's all we ever ask. All right, we've been there, done that. Every one of your teachers has their GCSEs. We remember what it was like. No, we didn't have to deal with a COVID situation in year 10, but if you can cope with that and get past it, you will put yourself ahead of the rest of your year group across the nation. That's a good place to be. So, all the way back to where this started, what to do with your summer holidays, be honest with yourself. If you've left stuff and let it slide, you want to hit year 11 knowing I've got revision notes for everything. Everything I've done up to this point, I've got them. How many people would genuinely say they're 100%? Not yet. And that's the honesty part that I was asking for earlier. And if you sit down and go, all right, I've got a week to go, or I've got this week, and go, I'm going to make sure I can have as much fun during the summer holidays as possible. I want to work out exactly. So go home tonight, work out exactly what you're missing. Just draw a list up on the wall, and then you do them one at a time and just cross them off. I haven't got any notes for P10 electricity that we're doing. All the stuff we did for science is still up there. So you can go and find the YouTube videos. Okay, and then you go P10, done, crossed off the list. Then you go English. I haven't done much on poetry as much as I should have. So I'm going to do some work on poetry, then you're going to cross that off the list. So you make a list and you cross them off. And you be honest with yourself. If your list is really big, you need to put more hours into it. If your list is really small, you just allocate what you need to get done. Am I talking gibberish, or does that make sense? Makes sense? But you got to be, guys, it always comes down to honesty. If you start lying to yourself, there's nothing we can do to help you. If you start saying, I'm going to get a 7, you know, across all my subjects, but I'm not going to do any revision work, we'll try and tell you you're wrong, but if you've convinced yourself of that, there's not a lot we can do to help you. Okay, so honesty is the first point. Right, that is the right-hand rule. Without giving it away, what do you reckon the next one is? Hey, there we go. I hope it's the next one, otherwise I'm just going to feel... Hey, it is a left-hand rule. Okay, so left-hand rule gets a little bit more complicated, but it links into Bill. Okay? So the right-hand rule is Bill. So, sorry, left-hand rule. Everybody pause. Before you start drawing, get your left hand out. Now, I struggle to do this, so go with me a little bit. My left hand doesn't work as well as my right. It looks like that. So every finger, is 90 degrees to every other finger. Okay, so it would look like my thumb is going up on the board, my finger is going along the board, and my middle finger is coming out of the board. Does that make sense? So everything's 90 degrees. I can see most. Can everyone show me that they're doing it? Because if you get this bit wrong, it gets really complicated. Yep, good. So that's really hard to draw. I accept that. Have a crack at it. But more importantly, make sure you label thumb for thrust. It's our force. Forefinger for field. Middle finger for current. Okay? Middle finger for current. So hopefully you could hear most of my voice from over there on the screen. For those of you at home, have a go at drawing this, or you could cheat and Google the image. It doesn't really bother me, to be honest, as long as I see this on your revision notes. If I am looking at someone's P12 and P13 notes and don't see Fleming's left-hand rule, and can we put a little subheading as well once you've drawn this? Fleming's left-hand rule, because this, label the whole thing up. Oh, you don't need to write all of that after it. Just make sure you draw the hand, label it as Fleming's left-hand rule, and label the thumb, forefinger, and middle finger, please, as thrust. It's force, but we call it thrust because it shares the same two letters as thumb. Helps people remember which one's which. And we're going for time, not too bad. Oh, no way. Never saw them.
My neighbour was born down this way.
Your neighbour was?
That's 8 o'clock in the morning.
That's not the worst thing that can do. That is pretty early to be mowing the lawn, to be fair. You're going to tell me you're still asleep in bed, won't you?
Yeah, I thought that was
No, it's not so bad. I don't want to know where that joke is going. Okay, so we're just going to go on to the next slide because I can't remember what it is, and see if it's the question that will make this make more sense. Okay, so now that you've drawn the left-hand rule, now I want you to draw something really simple for me. Okay, I want you to draw. Now you don't have to do it in 3 dimensions, but it does make it easy to see. So in this instance, we have a north of a magnet and a south of a magnet. We've made a magnetic field by doing that. Which way is the magnetic field going to go? Same as on the Earth. Which way does the magnetic field go?
North.
North to south. So it's going to be straight lines straight across. I'm going to draw that over the top. I think that'll make more sense. So we're going to draw a magnetic field. Okay, so our magnetic field is going to go across this way. And I'll label that as B. Our current, so in this case the wire is actually coming out of the board. It's quite hard to draw that in 2D, so I've gone for a slightly 3D looking diagram. Current coming out of the board. I would like to know which way the cable's going to go. It will not want to be there. Now I would have normally done this as a demo for you to show you, because the wire will move. It won't be happy to be there. But we can't do it as a demo because it's all in the lab. So now you have to take out your trusty tool that you're all born with or have in this room, thankfully. I'm going to be cautious. I might have a student one day who doesn't have a left hand. So could you all take your left hand? Okay, so we want to know what the resultant is the thumb. We want to know the force. Okay, so that's the answer. So we need to line up the other two. Forefinger for field. Which way is our field going? That way. Everyone point your left finger, your forefinger going across the board, please. Which way is the current going?
this way.
Which is out of the board? So everyone's middle finger pointing out of the board, please. Where's everyone's thumb pointing? Where's the Y going to go? Up.
Oh yeah.
That's it. That's the answer. So someone's just had their light bulb moment in there. Okay, so all we have to do is take our hand, and I do not feel conscious of people looking at you during a test. Every P13 test or paper 2 test with P13 in it, I have seen students in the middle of their GCSE exams with their left hand out doing this all the way around the it's the physics gang symbol, okay? It is well renowned, okay? Only special people get to use it, all right? Don't tell anyone. And the Fleming's left hand rule, there's nothing to stop you in an exam using your left hand to figure out where things are going. They'll probably look at you a bit funny, but any physicists will know exactly what you're doing. Okay? So, that's an easy one. Now, some of the questions. Okay, so the questions are exactly as I led us through. So, for those of you at home, if you lined everything up, you would find that the force, or the thrust, would be up. Okay? Should we try a different one?
Yeah.
Okay. There's a few parts of this, so we're going to do it as a team and figure this out. What's a Y going to do if I just dangle it in the air? It's going to fall, right? Why is it going to fall? Why does anything fall? Gravity, okay? So, we've got a Y with a mass of 35 grams. What's its downward force? Okay? What equation are we using? I'll give you a hint. Newton's second law. It's the only equation in there. We've got force, we've got mass, and we got, what's the A stand for?
Acceleration.
So
Mass time.
what equation's that?
Mass time. Force equals mass times acceleration.
Okay, force equals mass times acceleration. So we need to know what the downward force of that piece of cable is. So I've written the equation down. What do we do next? Everyone write the equation down. What do we do next? Got an equation. Do we need to rearrange it? Do we? No, we've got it's force equals something, so F is the subject. We'll leave F where it is. So we don't need to rearrange it. What's the next step in a physics question? Substitution. Well done. So, what's the trap here, Will? Just checking you're still with us and awake. Can we put 35 grams into that? Substitute that 35 grams straight in? Why? What are we working in physics? What's our mass all measured in?
Millisecond.
The mass.
Oh, grams.
Not grams, bigger.
Newtons.
Newtons is force. You're on the right track. What he just said.
Oh,
Kilograms. Okay, so we need to put 35 grams in as kilograms. So can anyone do the conversion for me?
0.35.
0.035. What are we going to use for acceleration? Tells us in the question. 10. Okay. So we probably don't need a calculator for that. There we go, guys. That piece of wire is going to have a force of 0.35 newtons down. Not the most exciting thing in the world. But how do we make it not move? What can we do to that piece of wire to stop it moving? Just make it hover. What would we have to do? If you wanted to run this way and I wanted to stop you, what would I have to apply to you? How much force? The same. Okay, well done. So if someone's falling and I want them to hover, I have to push back. Has anyone seen indoor skydiving? Yeah? Well, those people are still falling the whole time. There's gravity. Well, they're not falling because their net force is 0. So the amount of air coming up through the floor has to equal the same amount of force as what they're applying downwards. Yeah.
I've always wondered this about like indoor skydiving. So you get people just standing on the fan whilst the others are flying about.
Yep.
Why? How?
Okay, so what's the difference with their shape?
People like
Streamline. What's the word streamline mean?
Straight.
that's when,
Okay, so what would be the difference if I lay, I'm not going to do this, if I lay it out on that table, how much surface area would I fill up covering that table versus if I stood on it?
A lot more.
A lot more. Good. So what's actually happening is when you're flat, all those air molecules are hitting lots of your surface area. So you've got more force from the air molecules acting up. As soon as you, in fact, so when I was taught to skydive, you didn't go feet first because I don't think I was ever good enough. We went head first. And when you went head first, you'd accelerate really rapidly. You get to a certain point, you can go any faster. But the difference between being flat and being streamlined was huge. So we'd go head first to go faster. That's why you see some people sitting on the grate. They will almost, and I've never tried this in indoor skydiving, but you do see them bouncing around like they're walking on the moon. So there's still a lot of force from the air coming up, it's just not enough to overcome their force due to gravity. That make sense? Cool. That was a sideways plot I didn't see coming. Right, so we've done part one. Congratulations, you've walked through with me for part one. For part two, we need to use an equation from last week. What equation? Fred and Bill. Good, we've had that from the class. What's the equation? Actual equation, please.
F equals B
Times L. Okay. So do we know the force? How much force do we need? The same, which was? We just worked it out, still written on the board. Okay, so now hang on, we need to, my mistake. I got it wrong for once. We've written the equation, what do we need to do next? No, we need to rearrange before we substitute. You can do it the other way around. I just generally find most people make less mistakes when you rearrange because it's simple to rearrange at the moment. What do we need to make the subject, please, guys? What's the question asking us for? Current. So which letter is that represented by? I. So we need to make I the subject. Do you want to talk me through it? At that point you paused. Anyone want to help me through it, Sophia? How do I get I on its own? What have I got to get rid of? Okay, are they all multiplied or added together? Okay, what's the opposite of multiply? Okay, so we're going to divide it by the ones we want to get rid of. So we're going to divide it by B and L, which you're quite right to get rid of. If I divide that side by B and L, what must I do to the other side? Hang on. I have it. Okay, so we must do exactly the same. So B and L, that's meant to be a B. Right, if I've got B top and bottom, what can I do with those? Get rid of them, cancel them out, absolutely. What about the L's? Same, and now I'm left with I on its own. Well done, you have made I the subject. I'm going to rewrite it out just to make it a bit neater for us. So I equals F over B and L. Okay, so force, what's our force? Now we're going to substitute in. So hopefully there's people writing this down so they can put it in their calculator straight away. What's our force? We did it from part one. 0.35. And what is the magnetic flux density of our magnets? 4.5. And what's the length of wire in between them? 0.1. And hopefully you have now worked out a tier 7 question, because this would be evil.
Is it 0.777?
I don't know, you tell me, you got a calculator.
Oh, yeah, it's 0.77.
Okay, got 0.77. Anyone got anything different? Will, what'd you get? You haven't put it in yet?
No.
Practice putting it in, please. Amelia, put it in yet? 1 sec. Okay, there's a few people catching up. Tom, so have you actually written it all down though?
No.
Can you please write it all down? You need, before you touch your calculator, and I know this is going to sound pedantic, it is worth marks writing down what you put in your calculator. If you get it all right, you might get all the marks anyway. You make the tiniest mistake, you'll get nothing unless you've written it down. So before you pick up your calculator, write it down. What'd you get, Amelia? 0.77 or 0.78 if we round it up to 3 significant figures, 2 significant figures even. Same.
Is that right?
Oh, we've got 2 people with it so far. Yep, 0.78. Okay, looks like a fairly. Put in your calculator yet? Practice putting in your calculator, guys. Come on. I know it sounds like I'm teaching you to suck eggs. That means being pedantic. It's an old saying. It basically says, I'm making you do something you already know how to do. But this isn't about telling you how to do something again. This is literally telling you to practice. Okay, that's all. It was like that question earlier in the lesson where I asked you to do the standard form into a calculator. The amount of people who make mistakes doing that because they just don't practice enough. Yeah.
You know, at the top and bottom of there, when you squeeze it and things don't break.
Okay. I'll take your word for it. We need one last thing. We need a unit. What's a unit for current? Don't say I. I'll throw something in. It's not I. Okay, so it's not obvious. What's a unit for current? What would you measure it with?
Is it Q?
Hold on, no. Current. So in physics and science, when you're measuring things in a circuit, you would have used a voltmeter and something else. No, not voltage. There's a voltmeter and then there's another kind of meter that you would have used. This is how you remember it. Anyone remember it? It has a big capital A. What's the big capital A stand for? Good guess. No? Alright, so we need to be able to remember this. Current is in amps or ammeters. Okay, so capital A. Alright, now you probably wouldn't have to remember that by the end of this question. That's a monster. If you got that in a GCSE question, I'd love you to all have an attempt at it, but I'd just be happy that you had an attempt at it and you wrote out your equations, you rearranged them, and you tried to substitute in. But that's not straightforward, okay? But that's something that people actually have to do when they're using the Large Hadron Collider. So this is real science in progress. So when you've got a proton flying around near the speed of light, around a 26-kilometer circuit, you need to know the proton has some mass. It will want to fall. Okay, and you have to overcome that. Only a tiny bit. Its mass is tiny. It's almost insignificant, but you do need to know it. Okay, and they allow, because they've got giant magnetic fields all the way around it to hold the protons where they want them. Right. Any questions on that before we move forward? Right. I think we're at the end. So we've done the right hand rule. Everyone with your right hand. This is where people start doing Fleming's left hand rule with their right hand by accident. What's your thumb represent? What's your thumb doing? Go on. Have a look at your notes if you need to. Can't find it? Find it now and write it in. It's currents. Okay? And your fingers will represent what? The magnetic fields. Good. Everyone switch hands. Left hand, please. Oh yeah, I know. It gets confusing. Yeah. Oh, did you do? Oh, busted. I didn't catch you, so you got away with it. And you were honest about it. Thomas, which thumb going to represent?
Oh,
Thrust or force. Thrust the thumb, but it's force. Neil?
This is the current.
No, you had a 50-50 guess there, but you got the wrong one. Forefinger, other word that starts with F. It's not field. Not force, sorry.
Don't remember.
Don't remember? Have a look up. Help him out. What is it? Nice and loud. You're right, so be loud. Be brave. It is field. Okay? So remember we had the magnetic field going across. And lastly, our middle finger, you broke eye contact first. Current. Okay? So, what if our current was going into the board? What would we do? With that question before. So our current was our middle finger. If the current was going into the board, so on that, if I go back, I can't go back now because I'll overwrite. If our current was going that way and our field was going that way, so our field is going that way. So everyone do it with me, left hand. Field is going across the board, but our current is going into the board. Where would we have to point our middle fingers? If the current was going into the board,
Yeah, like.
That way.
Oh.
Oh.
this is where everyone gets twisty.
Wait, hold
So
on.
which way would the wire go now?
Hold on. Same. Wait, which way is that?
That way. Down.
It goes
Down. Yeah. So I'm just checking everyone's sort of followed along here. So you have to actually point with me, so your field is still going the same way. But if you make the current go the other way, the wire will go down. Okay? You're going to get a question like that in the next.
Do they
Let's-
ask us to draw that?
No, you'd just be asked to work out which way it would move,
Right.
or you might be asked to work out the force involved. Okay, so if you follow along at home, well done. I will see you in September. Please make sure you bring your books and notes from this year. This goes to everyone in the room as well. So you're not getting a new book first day in September. Okay, you bring your books from this year and you continue on with them, okay? And make sure your revision material is in the back of them. Okay, so when we ask you a question from P4, you're not all sitting there going, huh? Okay, I want you to be able to find P4 stuff and get it out. That's why we make revision material. I don't expect you to remember everything at this point. We need to be at that point a couple of weeks out from the exam. Okay, at this stage, we're just trying to make sure you've got all your ducks in a row and you're organised. For those of you at home, thank you very much for joining us, and we'll see you in September.